The LTE standards do not specify how much power the various channels and reference signals should use. It is up to vendor to develop the appropriate algorithms and controls. Power control regulates the transmit power of E-node BS and UEs to compensate for path loss and shadow fading, counteract interference between intrafrequency electron cells, and help meet coverage and capacity requirements. The goal is to maintain a constant energy per resource element, so that UE can use the reference signal power to estimate the other downlink channels. The power is not exactly the same in all resource elements since different modulation scheme require different power levels. Power boosting can be used to increase the power by 3 decibels on the reference signal. The PDSCH power can be controlled by varying the number of CCE that has used based on the reported CQI history. Downlink power allocation applies to the following physical signals: traffic channels, control channels, and messages using fixed and dynamic allocation. Fixed allocation, cell-specific reference signal, CRS. Synchronization signal PSS and SSS. Physical broadcast channel, PDSCH. Physical control format indicator channel, PDSCH. Physical downlink control channel, PDSCH, carrying common control information. Physical downlink shared channel, PDSCH, carrying common information. Dynamic allocation, random access response, RAR, messages. Physical HARQ indicator channel, FITCH. Physical downlink control channel, PDSCH, carrying dedicated control information. Physical downlink shared channel, PDSCH, carrying UE-specific information. CRS are transmitted in all downlink subframes. They serve as a basis for downlink channel estimation and are used for data demodulation. The CRS power is indicated by the energy per resource element, and is determined by the reference signal power parameter. The reference signal power parameter specifies the reference signal, RS, power output by a remote radio unit, RRU. For common scenarios, the RS power indicated in System Information Block Type 2, namely reference signal power SIB2 in the unit of dBm, is calculated using the following formula. 0.1 multiplied by the reference signal power plus 10 log of the number of physical antennas divided by the number of CRS port in the cell. The number of physical antennas in a cell is specified by the cell TXRX mode parameter. For 8T8R and 32T32R FDD cells, the RS power indicated in SIB2 is calculated using the following formula. 0.1 multiplied by the reference signal power. In PDSCH power setting, OFDM symbols in one-time slot can be classified into 2 types, Type A, symbols, and Type B symbols. Type A, PDSCH resource elements were not in the same symbol as reference signal resource element. Type B, PDSCH resource elements in the same symbol as reference signal resource element. As described above, the CRC power is defined by the reference signal power. The power formulas for the PDSCH type A and B are defined as follow. PDSCH type A equal rho A plus reference signal power in dBm, and PDSCH type B equal rho B plus reference signal power in dBm. The rho A is calculated as follows: if PDSCH data transmission uses transmit diversity with 4 antenna ports, rho A equals delta power offset plus PA plus 10 log 2. In other scenarios, rho A equals delta power offset plus PA. Delta power offset is specified by the parameter NPREO constant, acronym of non-PDSCHRS EPR offset used for CQI optimization. And PA is defined by PA for even power distribution parameter under cell downlink power control PDSCH PA. Rho B depends on the power factor ratio of rho B to rho A. The table lists the values of the cell-specific ratio rho B to rho A, corresponding to different PB values in scenarios with different quantities of antenna ports. PB is specified by the PB parameter under PDSCH configuration settings. To calculate the PDSCH power for channels type A and B, we need to calculate first the reference signal power, which is given by the following formula. PRS power equal the power per single port, minus 10 log of 12 subcarrier multiplied by the total number of RBs, plus 10 log 1 plus PB. The power per single port is RRU power divided by the number of antenna ports. An example of calculation: bandwidth 15 MHz. Antenna ports, 2. PA equals minus 3 decibels. PB equals 1. RRU, 60 watt. The power per single port is 44.77 dBm. Then the power per reference signal is 18.2 dBm. The next step is to calculate ρ A and ρ B. ρ A is equal to delta power offset plus PA, plus 10 log 2. When the UE receive a PDSCH data transmission using precoding for transmit diversity with 4 antenna ports. Otherwise, ρ A is equal to delta power offset plus PA. As described in the preceding slide, delta power offset is the NIPRO value used for CQI optimization. In this example, delta power offset is set to 0. So, the ρ A is the value of PA parameter in decibel, which define the difference between two dBm values. PDSCH type A power and the reference signal power in dBm. The power of PDSCH type A is equal to minus 3 plus 18.22, equals 15.22 dBm. To use ρ A as a ratio, to calculate the power in watt, then ρ A equal 10 exponential of PA divided by 10. And the power of PDSCH type A is equal to ρ A multiplied by the PRS power in milliwatt. The ρ A equal to 0.5, and RS power is equal to 66.67 milliwatt. Then, the power of PDSCH type A is 33.41 milliwatt. To calculate the power of PDSCH type B, we need to calculate the value of ρ B. ρ B depends on the power factor ratio of ρ B to ρ A. The table lists the values of the cell-specific ratio ρ B to ρ A, corresponding to different PB values in scenarios with different quantities of antenna ports. In our example, PB is 1, and PA equal to minus 3 decibels, and 2 antenna ports. So, the ratio of ρ B and ρ A is 1, then the ρ B value is 0.5 as ρ A equal to 0.5. The current value of ρ B can be used to calculate the power in milliwatt. For a calculation in dBm, ρ B should be converted to decibel value. The conversion formula is ρ B equals 10 log 0.5, ρ B is equal to minus 3 decibels. The power of PDSCH type B in dBm is given by the formula, minus 3 decibels plus RS power in dBm, equal to 15.22 dBm. The corresponding value in milliwatt is given by multiplying ρ B and the reference signal power. An other example, PB equals 0, and PA equals minus 3 decibels, and 2 antenna ports. From the table, the ratio of ρ B and ρ A is 1.25. The ρ A is equal to 0.5, the ρ B is 0.6264. Converting this value to decibel will give ρ B equal to minus 2.03 decibels. So the power of PDSCH type B is minus 2.03 plus 15.22 equals 13.19 dBm. The reference power is changed because of the new value of PB. The power of PDSCH type B in milliwatt is 20.88 milliwatt. The value of the PRS is 67.66 milliwatt, and the power of PDSCH type A and B are equal to 33.41 milliwatt. The view of the power level of each channel type. In this example, the PDSCH and PHICH power are equal to the reference signal power. To calculate the power for PDSCH type A and B in watt for all RBs, are given by the two formulas, which include the setting of the reference signal power, PA, PB, Rho A, and Rho B values, and the number of resource block in the allocated bandwidth. The formula of PDSCH type A is the power of the resource element type A, which is 12 subcarrier per RB. The formula of PDSCH type B is the power of the resource element type B, which is 8, and the power of two reference signals. An example of different settings of PA and PB, in a bandwidth of 15 MHz and an RRU of 60 Watt. The setting of PA and PB provide a ratio for the power level in PDSCH type A and B to the power of the reference signal. PA equals -3, PB equals 1. PA equals 0, PB equals 0. PA equals -4.77, PB equals 2. PA equals -6, PB equals 3. PA equals 1, PB equals 0. PA equals -3, PB equals 0.